Hi, everyone. So my name is Amy Cheng. I'm a web developer with New York Magazine, and I'm also an artist. Now, each and every one of you has also had personal experience making art. Maybe as a child you worked with crayon, or maybe you've picked up painting as an adult. And even if you didn't progress past the crayon stage, well, I have good news for you. If you know JavaScript, you can make art. So in this talk, we're going to recreate two famous masterpieces of modern art, a spot painting from the Spot Painting series by Damien Hirst, and a composition painting by Piet Mondrian from his composition series. And we're going to recreate these two artworks as a way to explore how JavaScript can be an artistic medium. And just like painting, we're going to start with a blank canvas. In the case of JavaScript, the blank canvas is the HTML5 Canvas API. So on the screen, we have a code that will allow us to draw a circle onto the screen. This line, canvas.getContext2D, basically initializes the actual interface that the browser is using to tell your computer to dynamically draw bitmap graphics to the screen. Here we have a draw function which contains instructions. And so with ctx.beginPath, we're telling our computer to get ready. We're about to draw something. The second line defines the kind of shape we want our computer to draw, and in this case, an arc. The last one, the third line, .stroke, is telling the computer, hey, I want my circle shape to have an outline. Then we have the entire draw function being passed as a callback to request animation frame. Request animation frame is basically a smarter set interval function. So the callback will not be executed until the current DOM repaint finishes or the current animation finishes. Another bonus to using request animation frame over set interval is that if your browser tab is not in focus, that callback will not be executed. Another thing about request animation frame is that it runs continuously. So let's draw, in the previous example, we were just drawing one circle. So let's draw many, many circles to recreate a spot painting. And to help us, we're going to use a JavaScript library called P5.js. Now, P5.js was designed to be accessible to artists, designers, and beginners. It's actually an offshoot of the processing language, which is written in Java. Now, processing was created at the MIT Media program. And its creators basically had this intention to turn artists into programmers and programmers into artists, which is just perfect for our talk. And so P5.js has inherited this philosophy. Now, a disclaimer. My goal for this talk is to introduce you to concepts and not necessarily advocate P5.js. Those of you who have had more experience with JavaScript know that the ecstasy and the agony of JavaScript is that there are many, many ways to do the same thing. For example, on the screen we have, we're using 3 different drawing libraries that all use the Canvas API, but they're all kind of drawing the same circle. And even though, so the first block is P5.js, which I'm going to use in this talk. The second block is for Fabric.js, and the third is Easel.js. And even though we're using 3 different JavaScript libraries, we can still pass in arguments or call methods that will allow us to define the horizontal, vertical position of our circle, as well as the horizontal and vertical radius. And there's also a method or a parameter that we can pass in that will fill that circle with color. Now back to Damien Hirst's spot painting. So in a 1996 interview, Damien Hirst referred to a series of spot paintings as a sculpture to infinity. And he said, or has implied, that he'll just keep painting spot paintings until forever. And on his website, he lists about 90 of these spot paintings created between 1992 to 2012. So about 4 per year. During this talk, we're going to generate many, many spot paintings in just a few minutes. See that? So here's one spot painting. Here's another, and another. As you can see, they're all kind of a little bit different from each other. And we've just generated 5 spot paintings in under a minute. So let's look at the code. So P5.js requires a setup function, and this setup function runs once at the start of code execution. In our setup function, we have a create canvas method, and what this create canvas method does is that it creates a canvas HTML element and appends it to the DOM. And so our canvas element is going to be 800 pixels wide, 500 pixels tall. The next line defines the background of this canvas, which is going to be white, and no loop. So request frame animation runs continuously, and in P5, the draw function, which is also required, is being passed into this request animation frame, and it's running continuously. So what no loop does is it's telling P5 to only run this draw block once. You'll also notice that there are two nested for loops. The first for loop allows us to draw a spot across the screen, whereas the second for loop allows us to draw a spot down the screen. Sorry. So we have a color method, which I'll go into later, no stroke, which means we don't want our circles to have outlines, and the ellipse method, which basically wraps all the native JavaScript I showed you before into one convenient method, and we're setting the horizontal, vertical position, as well as the size of the circle. So in our color function, we're using something called the fill method. And what the fill method does, it accepts either 3 arguments or a color object. And then it takes this color and fills any geometry that is defined after the execution of fill with that color. You'll see that for each of the arguments I'm using random to generate a value. And what each of these arguments mean depends on the color mode we're using. So P5's default color mode is RGB, which stands for red, green, and blue. And so the first argument refers to red, the second argument refers to green, and the third argument refers to blue. And so we're basically defining how much red, green, and blue makes up this color. But as you can see, we're using random to randomly generate a color. And what I've just sort of demonstrated here is that JavaScript is an artistic medium that can do procedural generation. And here is the procedure we're using to generate the spot paintings. Now let's go back to the original and compare it to our own. Now, I feel that our spot painting isn't too faithful to the original in terms of color. So in order to get our spot painting closer to the original, I'm going to turn each of these arguments of the fill method into a parameter that we can tweak on the fly without having to go back to our source code. As I mentioned before, the default color mode of P5 is RGB, which stands for red, green, and blue. But I'm going to switch the color mode to hue, saturation, brightness, HSB. So imagine a color circle. So the hue aspect of a color refers to a point on this circle, and saturation and brightness refers to how far away or how close this point on this circle is towards the center. And as you notice, the center of the circle is pure white. So what we have here is a GUI, which is which I created using a library called dat.gui, dat.gui, which is a straightforward UI library released by the Google Data Arts team a few years ago. And here I have a drop-down that allows me to quickly change color modes. I also have sliders, which lets me change the range of numbers that our random function is using, as well as checkboxes that control whether or not I want that argument to randomize in the first place. So we're using HSB mode because it will allow us to more intuitively change the lightness or brightness of the color. So let's not make hue and saturation random. Now we got something super duper bright. But that's not quite what we want. We want it to be a little duller. I think that's close enough. But let's say you don't really care to be too faithful to the originalness. Let's say you just want to play with different color schemes. It was something a little bit more monochromatic, switching back to RGB mode. Let's freeze the blue value. So in parameterizing the arguments of fill, we're exploring many possibilities dynamically. So let's look at the code. So what we have here is we created a JSON object called machine state, and our UI is able to manipulate the properties of this JSON object. Then the properties of these JSON object is passed into a refactored color function, which our color function then takes to generate a color. We're still, right here, we're still relying pretty heavily on random. So let's see what happens when we use random on other visual elements of artwork. So we're using random to determine the size of each spot, as well as the position of each spot. And so we also have this color array with a limited set of colors, but we're using random to randomly pick out a color. So what we just did here is created an homage to the Obliteration Room, which is an installation by Yayoi Kusama. And the Obliteration Room starts off as a completely white room, and each visitor to the room is given a set of colored stickers, and they're allowed to place the sticker wherever they want in the room. However, even though I said we're randomizing different aspects of this picture, you'll notice that the spots are kind of clustered towards the middle. Well, that's because in our code, instead of using the random function, I'm using something called random Gaussian. And here's the source code. So random Gaussian generates numbers according to standard deviation, which means that it will more likely generate a number closer to the mean of a range of numbers. What that means is, given a range of 1 to 100, random Gaussian will more likely generate numbers that are closer to the average of all the numbers between 1 and 100, 1 to 100. You can also pass in SD, which stands for standard deviation, and the larger number you pass in, the more likely random Gaussian will generate numbers farther away from the mean. And here's this bit of map that JavaScript is using to generate those numbers. And one way of viewing what JavaScript is doing in this case is that it's painting with algorithms. So on the screen is a mathematical formula for Mandelbrot fractals, which are shapes that could be found in nature. Now, I believe that mathematics is one expression of the world, and art is another, and that computation can serve as a bridge between the two. So here's a JavaScript app created by Christian Sigen Larsen. He is not using any libraries as far as I can tell. It's all native JavaScript and the canvas element. And in this app, we can explore this fractal. And JavaScript is generating the fractals, well, kind of on the fly. I think it's because we're too deep into the fractal and the math just gets harder or takes more time to calculate. Well, you get the idea. Another way of viewing the work we've just done is that we've created a system using JavaScript. And as you saw in Arena's talk, and if you have experience developing web apps, JavaScript is perfectly capable of managing many disparate parts to create a more complex whole. So if we look at our spot painting, we can consider the parameters, the random function, the color function, ellipses, the GUI as disparate parts that make up our spot painting generator. In our homage to the Obliteration Room, we have more ellipses, random Gaussian, and color array. So let's be a little bit more ambitious with the art systems that we're creating. So let's recreate a composition painting. we have our old friend random, and we're using the random function to place our rectangles anywhere on the screen, as well as picking out a color for each rectangle and determining the size. You'll notice that our composition is not that faithful to the original. And while we could spend some time writing additional logic to get our composition closer to Mondrian's composition, I feel that's kind of underutilizing what JavaScript can do for us. What if we turn each square or each rectangle into automata? Here's another example. In this example, the yellow square is following the blue rectangle. And just like the genetic automata in the previous talk, we wrote some simple rules that come together to create kind of a simulation of more complex behavior. So here's our code. So basically, each Mondrian rectangle is a cell. And upon initialization, we are picking out a target location. And this target location is represented as a vector that's randomly generated. And so this target location refers to a random point on the canvas. Then we have this update function where we're doing a bunch of vector math to figure out how far away our rectangle is currently from its target location. And then we have all this math going on to figure out how much farther our rectangle has to go. And as you can see here, the update function is run every draw, each time the draw function is executed, which is happening continuously because it's being passed into request frame animation. And what's happening here is that we're creating animation. Each time the callback is executed, we have one frame of animation. So at each frame, we are constantly figuring out whether we're constantly trying to get our rectangle closer to its target location. And once it's reached its target location, a new location is created. Let's look at a more complex example. Here's our spot painting as a flock. So this is just a modified flocking example. I'm using Daniel Schiffman's code, which he wrote for his book, Nature of Code. So what's happening here is that each spot has a set of rules governing its behavior. We have a function with some logic that kind of simulates seeking behavior. So each spot is seeking another spot. Then we have separate function, which is basically just contains collision detection. We want our spots to be kind of close together, but we don't want them to collide. And align and cohesion makes sure that all the spots are kind of following a path that mimics a flock. And so in this previous example, we've sort of created automata that interact with each other to form a system. And so far with the spot painting, composition automata, and with our homage to the obliteration room, we've explicitly kind of written rules in JavaScript for our code to follow. But what if we could create a system that could write its own rules? This is what machine learning is all about. So machine learning is all about systems that can learn from its inputs. You would give data to this machine learning system and don't tell it anything else, and it will just figure out what to do with this data, or what kind of rules determine this data, or affect this data. So let's watch code paint. Double checking something. Okay. All right, so what could our code be painting? It's me. So you'll notice that what the code just painted doesn't look exactly like the photograph, and we could write some code to get the code's painting looking more exactly like the photograph. But I feel like what the code gave us, it has a modern art quality, and it's more expressive of how JavaScript sees the world. So what's happening here is so here are some code paintings the code did a little beforehand. You'll notice that they're all kind of different, but kind of similar in some ways. So I'm using a machine learning library implemented in JavaScript called Synaptic.js. And what's happening here is we've initialized a computational model of a neuron called a perceptron. So we have something called var image data equals get pixel data. And this is basically a function that wraps logic for getting canvas data. And if you were here for Mariko's talk, she does that to do her image processing stuff. So we're using the same exact logic, except we're not manipulating pixel data, we're just gathering information. So we have information, so I placed the photograph onto a canvas element. I'm using get pixel data to get information about each pixel of that photograph. Then I'm taking this pixel data into the iterate function. And you'll notice there are two nested for loops. So what these nested for loops do is examining the horizontal and vertical rows of pixels of this image. And we have an activate and propagate function. So what's happening behind the scenes in the activate function is that our neuron is examining the data. And there's a bunch of math happening. And this math is basically formulas that kind of are science's best guess at how an actual bioelectrical signal goes through a neuron. So in the activate function, our neuron is looking at the data. And then we have propagate. And in the propagate function, our neuron is making guesses as to what color each pixel should be. So given a pixel at location 100, 100, our pixel makes a guess, and then it's corrected by the actual data. So it's learning from its mistake in the propagate function, and then is adjusting its guess each subsequent iterate function. You'll notice that I'm passing iterate as a callback in request animation frame. So in our preview function is where the actual painting is happening. We're basically just overriding canvas data with the neuron's best guesses as to what color each of those pixels should be. So what I've just demonstrated here is instead of following rules blindly, our little neuron is figuring out the rules on its own. So to take this even further, we have deep style transfer. So on the screen right now is a screenshot from a paper called A Neural Algorithm of Artistic Style. And basically, the authors of this paper have created a convolutional neural network, which is basically many, many layers of many, many neurons. And they're feeding a painting into the system, and this system is learning about the distinct features of this painting. And then our authors are passing in a photograph, and our system is learning about all the distinct features of this photograph. And then our neural network takes what it's learned about both pictures and combines them into a single image. Now, I have bad news for you. JavaScript is not ready for this just yet because the math required to do all these calculations is pretty intensive. If you're to do this on your own, you need some like super duper souped up video game machine because the code requires access to the GPU. JavaScript is not there yet. Maybe at the next Nordic.js it will be. We'll see. But regardless, I hope you can see that code is an art medium, but it can also be an artist collaborator. So instead of a studio assistant that follows your directions rather unquestionably, it could be a partner in making art. So here's a collaboration. It's taking a while because it's learning about the photograph. There we go. So the decisions that our code is making is what color we are using, where to place each spot, And the decisions that I'm making are, oh, the color should be a little translucent, and once in a while, add a speck of red. So to review, JavaScript is an artistic medium that can do procedural generation, parameterization, painting with algorithms, creating and running systems, and doing self-learning. And throughout this talk, you'll notice that the reasons why JavaScript is a unique medium might apply to other programming languages. So what distinguishes JavaScript from other programming languages? I feel that what distinguishes JavaScript is that the iterations are cheap. There's hardly any compile time. You make changes to your source code, and you can almost instantaneously view it in your browser. And this will allow you, as the artist, to constantly refine your ideas inexpensively in terms of actual cost and time, inexpensively refine your ideas and constantly iterate on your work. Another thing that I think distinguishes JavaScript from other programming languages in terms of making art is that it's available to anyone with the internet. Once you're done with your artwork, you upload it to the web, and anyone who has a connection can view your work. They don't have to download and install your program. They don't have to physically go to a gallery to see your work. Another thing I want to talk about is this list might not be complete. I might not have gone through all the reasons as to why JavaScript is a great artistic medium. And I would invite you to kind of explore even more reasons about how JavaScript can make art. And if you go down that road, if you continue to play around with JavaScript as an artistic medium, I would also like to remind you that art is not an app. What might be a critical bug for your minimal viable product might actually yield interesting aesthetic effects. And so I hope this talk has gotten you excited about the possibility of making art with JavaScript. So I would like to thank you, and thanks for having me here.